Uh, Thanks everyone for joining the first webinar of a new series that we have launched, and we'll talk about that in a bit more. So let's get going. So this one, we are going to talk about Kubernetes. We are going to focus on the cost optimization, performance, and security aspects in the GKE. So that's where we are going to deep dive on. The webinar is going to be highly technical in nature. Hopefully, you guys will enjoy it and learn something new out of it. Yeah, so quick introductions. My name is Pawan Danani. I run the cloud consulting business for Clears UK in the UKI kind of market, and I'm based out of London. Alfred, do you want to do your
Yeah.
introductions?
Hi, good morning, everyone. My name is Alfred. I'm a lead cloud architect at Sears. I'm certified as an architect on both AWS and GCP, and I'll be handling the technical aspects of the session. Over to you, Franco.
Hello, my name is Franco Camba, and I work in Google Cloud as a customer engineer. And what I do, I help customers and partners in modernizing applications and infrastructure using Google Cloud Platform.
Awesome, thank you. A quick run through of the agenda. So just in terms of who we are, so we are Sears. We are a niche cloud engineering business, and we were born in cloud from day one, right? So the business was set up around 14 years ago, starting with G Suite, and then moved into Google Cloud Platform and Apigee and a lot of other kind of GCP areas. And we focus mainly with working with digital natives. So we work with likes of Flipkart, which is a huge unicorn out of India, and likes of Flipkart in other regions like SCA as well. So that's kind of our sweet spot. We specialize in infra and app modernization, data management, and data lake. So that's kind of core to us. That's what we kind of excel at. We are also multi-cloud business. So we are a Google Cloud partner, but we are also AWS partners as well. And above all, we are all engineers, right? I'm an engineer as well. The people from that we have in support functions like marketing, they also come from engineering backgrounds. So we are all engineers in different kind of grays of shades of gray that we have. So as I said, we have been in the business for 14 years in the cloud consulting business. We have 14 locations spread across APAC, UK, and US, and 2,000 plus customers across 10 verticals. So that's a quick run through of Sears, just so that you get some perspective on where we are coming from. At this stage, I'll hand over to Franco to take us through the key takeaways from the seminar. Over to you, Franco.
Yes. So during this presentation, we want to essentially cover three, let's say, main topics. And just as a reminder, all of these will be around essentially how to efficiently run Kubernetes, especially Google Kubernetes engine within Google Cloud. So the first thing we want to cover is what we call PVM, which stands for Preemptible Virtual Machines, and actually how to leverage them to reduce dramatically your infrastructure costs. Second thing, we want to actually to give you some tips about actually how to ensure that these veritable VMs actually run all the time and reliably. And finally, we want to actually cover a little bit of security aspects and new features that we added on top of GKE, Google Kubernetes Engine, for securing your cluster. Next slide, please. Let's make a step back and then talk about why Kubernetes and what it is and why it's now becoming more and more important. So as you may know, at Google, we start several billions of containers every single week. Containerization is something that allows development team to move fast, deploy software very efficiently, and operate at a very large scale. And you actually experience containers every day because Gmail, YouTube, Google Search, almost everything at Google runs in containers. So with Kubernetes, we put our internal experience in managing containers at this scale and actually share it with the outside world with this open source, essentially, which is Kubernetes. And with Kubernetes, what you can do, you can essentially automate container orchestration. You can manage your machines and services. And with all of this, you can actually improve your reliability and reduce the time and resources that you need to spend on things like DevOps. So essentially, it makes everything associated with deploying and managing your application easier. Other things that Kubernetes do is automating rollouts and rollbacks, monitors the health of your services, and actually you can prevent bad rollouts before actually things go bad. It can continuously run health checks against your services and can automatically restart containers that fail or have stalled, and only, for example, advertise services to clients when actually they have basically confirmed that they have started up successfully. And additionally, Kubernetes will automatically scale your services up and down based on utilization, ensuring that you're only running what you need and when you need it. And as a final point, if you're familiar with containers, also Kubernetes allows you to declaratively manage your cluster, allowing you to set up to be version controlled and easily replicated. Next slide, please. So we now discuss about Kubernetes. With Google Kubernetes Engine, or also short for GKE, we have a managed version of open source Kubernetes that is available within Google Cloud Platform. With GKE, we offer our customers basically the management of all the tedious tasks like cluster creation, like node upgrades, like automatic infrastructure provisioning, and give at the same time the same level of control of basically the open source standard Kubernetes. From your Google Cloud Console, you can create and start a Google Kubernetes Engine cluster in minutes. And when you create it, Google automatically provisions the virtual machines, the storage, and all the infrastructure services needed to run the cluster. It's very important to know that GKE is fully integrated with other cloud services, for example, with our global Google Cloud Network, our VPC network. And this allows actually the exposure of your Kubernetes application to the world via layer 4 and layer 7 load balancers. One last thing, we not only manage Kubernetes for you, but we also provide, and you will see throughout this presentation, a great number of advanced features, such as automatic service mesh deployment, cluster monitoring and logging, and a number of security features that make GKE an enterprise and production-ready solution. And with that, we are ready to talk about Knollscape.
Thank you, Franco. I'm going to begin by setting the context about this live case study that we performed. So this was for an organization called Knollscape, and they're an edtech startup that serves as a digital end-to-end learning and assessment platform for accelerated employee development. So just to give you some background, right? So these guys were initially on Azure using AKS, Azure's Kubernetes service, right? They weren't too happy with the trade-off with cost and performance, hence they decided to migrate to AWS. So the architecture here, although it's a little, it's not very clear, not really relevant. I'll explain a bit about it to you. So this is the architecture that they were having on AWS, right? So it's a standard 3-tier architecture, despite the fuzzy details. You've got a L7 load balancer serving traffic to containers running in ECS. They've got Redis for caching there, and you've got a RDS MySQL database in the backend. Now, the challenge that they were facing here, right, is while they were also on ECS, they were also evaluating EKS, which is AWS's Kubernetes services. And at that's the point we actually started interacting with them. And it's a good thing to note that when we started our discussions with them, they were already fatigued from their previous migrations, right? And when I look back on it today, I always think of them as the Goldilocks customer. So if those of you are familiar with the Goldilocks story, right? So the Azure porridge was too hot for them, the AWS porridge was too cold for them, and then they move on to the GCP porridge, and it's just right. But getting there was a bit of a challenge, right? Because our first interaction with them, they were very straightforward and blunt with us. They're like, look, we've already performed a migration before, right? If we are going to even consider moving to GKE or GCP, these are the things we are looking for. So first and foremost, we need a substantial cost reduction, right? Because without that, our discussion is not going to proceed anywhere. Secondly, the kind of applications we run, they're running kind of like cognitive gaming applications, right? So aside from their other assessment platforms. So it's essentially a 0% downtime application. So a second key point of theirs was that we need to ensure availability and reliability, while also maintaining scalability. That was another challenge they were facing, right? Scaling thoroughly on AWS. And thirdly, this is an important aspect for everyone, regardless of cost and performance, it's security. So I'm going to walk us through about how each of these challenges were addressed and how they were resolved. So step one is actually reducing the infrastructure costs. And we cannot get into a discussion about reducing infrastructure costs without talking about PVMs. So Franco actually gave you a bit of an overlay about what PVMs are. So I'll explain them in more detail in the upcoming slide, but this graph here is just to show you, what kind of cost differential you can expect by utilizing preemptible nodes, right? So as you can see here, there's a substantial reduction in cost just by actually going ahead and utilizing preemptible nodes over on-demand nodes. So the obvious question is, what is a PVM? What is a preemptible node? Okay? A preemptible virtual machine, or PVM, right, are virtual machines which are up to 80% cheaper than regular instances. Now that is a huge discount, right? So there's got to be a catch, and there is a catch. There are a few caveats here. So one of the caveats is that these machines are short-lived. They have a life cycle duration of 24 hours. Post these 24 hours, the machine will get terminated automatically, right? Secondly, their preemption is entirely dependent upon the demand in a particular data center. So say you're using the London data center, right? If there is a very heavy demand for on-demand resources, on-demand virtual machines, then Google has the right to actually preempt your virtual machine, take it away from you, and provision that resource to someone who is requesting an on-demand virtual machine. So there is no SLA, or no reliability, no availability guarantee that a PVM provides, right? And how do you actually use a preemptible node in GKE, right? So when you can actually create a node pool and you can enable preemptible nodes on that node pool, so that an entire node pool gets filled with only preemptible virtual machines. But if you do remember, I mentioned earlier, right? It's supposed to be a 0% downtime application. And here it's clearly mentioning that there is no guarantee on the availability and reliability. And that's what's so interesting about what we're going to explain. You can actually kind of cheese the system, use these different tips and workarounds to actually leverage PVMs to the best of your abilities, get that cost reduction without having to compromise on your availability and reliability. So before we get into that discussion, a good starting point is a decision map, right? To preempt or not to preempt. So this actually explains what kind of workloads are fitted for preemptible pools and what are not. So if you have like a stateful application, or you have a workload which has a static load, it's fixed, you know what to expect, in that case, a preemptible pool might not be the best fit for you. But if you have, say, a dev environment or a continuous integration environment, or QA and testing, or a stateless application as well. And when I say stateless application, I don't mean, it doesn't have to be purely stateless, right? As long as the session state is stored externally to the pods, right? As long as it's perhaps stored in a Redis or a MongoDB cluster or instance, that can also be considered stateless. And you can also incorporate these into, your web applications, your backend applications with load spikes, batch processing workloads, analytics workloads, machine learning workloads. We often see some of our customers actually leverage preemptible GPUs, right? So you can actually get GPUs with the same advantages of a preemptible machine, and of course the same disadvantages as well. But you're getting that heavy compute for a lot more discounted price, right? And of course reduced availability. So once you actually looked at this diagram, right, and decided, do I or do I not want to go for a preemptible pool? That's when we go into the next step, right? So we were actually able to achieve a 24% cost reduction in monthly cloud infrastructure spend by utilizing PVMs. That is not a nominal amount. That is quite substantial, especially when you consider their overall billing, right? This is a big chunk of discount. So the thing here is, like I mentioned, there are a lot of challenges that had to be addressed, right? There is no availability, there's no reliability you get with these PVMs. But there is a way we can actually overcome all of these issues and address them one by one. So I'm going to talk you through about some of the challenges that we faced with this customer, right? So the first challenge we faced was an increase in downtime due to frequent preemptions. Another challenge we faced was mass service disruption, underutilized preemptible nodes, and even downtime due to the uneven spreading of pods. So let's talk about the first challenge, increasing downtime due to frequent preemptions. Now, you have no control over the frequency of preemptions. That is entirely dependent upon the demand on a particular data center, right? So the simplest solution, albeit it's not a foolproof solution, is to just keep your workloads in a region where the preemption rates are less frequent. And if you are not constricted by data residency laws or if your primary user base is not within that region, right, you have no latency worries, then this is not a bad solution for you. But it's not the best approach, right? There is a better way to deal with this. And the better way is actually using a combination of on-demand and preemptible node pools. So here you can see we actually have two node pools, one for on-demand and another for preemptible node pools. And what you have to do is ensure that at least one replica of each deployment or job is maintained on this on-demand pool. So even in the worst case scenario, right, there's a preemption apocalypse, all of your preemptible VMs are down, right? Your on-demand nodes are still up, and that one replica is still up. So you will never get that 404 error. It's true, I do concede the fact that you will have to suffer from some performance degradation due to the fact that you have a single replica supporting the load of what 5 or 6 replicas were supporting before. And there's actually a way to address that also. So what you might want to do is on this on-demand node pool where you have that one replica, there is a feature on GKE, it's somewhat recently released. It's known as VPA, or vertical pod autoscaling. I'm not sure how many of you are already familiar with this, but this is different from horizontal pod autoscaling. It actually allows you to vertically scale up your pod to meet the requirements or meet the resource requirements that is being requested from it. So that single replica, you can actually implement a VPA on that single replica. So in that worst case scenario where all the PVMs are dead, right? Your single replica is actually going to be vertically scaled up to match the node. And when the PVMs come back up, which they always do eventually, right? The VPA will allow this pod to scale back down to its normal size. And that's as good as you can get there, right? That's the perfect match of cost reduction with availability and reliability guarantees. You don't even have to compromise on your performance degradation. Moving on to the second challenge, avoiding mass service disruption. So what is mass service disruption? So if you remember what I mentioned earlier, right, a preemptible virtual machine has a lifecycle duration of 24 hours. So say that no preemptions happen in this 24 hours duration. So let's take it from scratch. We've created 10 preemptible nodes in our PVM node pool. Okay, say we've created them at 12 p.m. today. Now this means that unless there are some preemptions which happen today, and let's just say hypothetically that no preemptions happen today, this means that 24 hours from now, that means 12 p.m. tomorrow, all 10 of those PVMs or all 10 of those nodes are going to get terminated simultaneously. This is the same thing as downtime, because this is essentially going to result in downtime, right? You have 10 nodes all failing at the same time, all terminating at the same time. Now, keep in mind, Kubernetes does restart these nodes for you. It does automatically by default, but the autoscaler will handle that. But that duration of time in which 10 nodes are all going down and the time duration takes to spin up those 12 nodes again, how do we address that challenge? And that can be actually addressed by using an open source tool called as the GKE Preemptible Killer, right? So this is created by a developer called Estafette, and we use several of their tools, but this is actually a very useful tool. So how it works is each node which is created has a creation timestamp, right? And the creation timestamp actually shows what time the node was created. What the PVM killer does is it annotates another timestamp, and it calls it the killing timestamp. So any time duration between 12 and 24 hours after the creation timestamp, what the PVM killer does is it goes ahead and manually kills that node, right? By manually killing that node, it's actually restarting its lifecycle duration. So you have another fresh 24 hours of node lifetime. And it applies this in a random fashion for all your nodes in the pool. So basically what this allows you to do is it actually ensures that all of your nodes are not getting killed simultaneously. It spreads the killing over a wide surface area so that disruption to your services is minimal. And this is a very essential service that you should be using if you're utilizing PVMs. Another challenge is underutilized preemptible nodes. So during our implementation, one day I got a call from the customer, and he tells me, Alfred, can you take a look at the node utilization? Take a look at the preemptible pool. And I went ahead and I took a look at it, and I noticed that all the preemptible nodes were severely underutilized. And quite to the contrary of what I was expecting, all the on-demand nodes were heavily utilized. And after some digging around, I found out that a lot of the pods had been scheduled onto the on-demand pool, and a lot of the PVM nodes were actually empty. And I was wondering how this had happened. And I realized that the reason that this happened is because we actually use a soft preference while scheduling, right? We use a preferred during scheduling option, which is a soft preference. And it basically states that look for PVMs, right? When it's scheduling the pod, it tells the scheduler, look for PVMs. If there are any available PVMs, then go ahead and schedule the pod on a preemptible node. However, if there are no PVMs available or there's a lack of resources, then go ahead and schedule that pod on an on-demand node, right? And so that's what was happening. But the issue was that once the pod was scheduled onto an on-demand node, it was never scheduled back onto the preemptible node. And because of that, right, because of this iterative scheduling process over time, eventually we reach that breakpoint scenario where your PVM nodes are being severely underutilized and all of your pods are ending up on the on-demand pool. So here we actually utilize this tool called a node pool shifter created by the same developer. And this tool actually, what it does is it actually goes ahead, it runs a checklist of your on-demand node pool, takes a look at all the pods. If it finds out that there are any pods which are scheduled on this on-demand node pool, and there is also space available in the preemptible node pool, right? It will go ahead and manually, it would automatically reschedule the pod onto one of the preemptible node pools. So this shuffling of pods always ensures that your preemptible nodes are actually being utilized, right? As long as there is capacity in your PVM node pool, this node pool shifter is going to be shifting the pods there, right? And last challenge we faced was a little tricky one, right? So if you can look at the screenshot here, I don't know how visible it is for you, okay? So because of this frequent shuffling of pods, we actually came across this scenario where if you take a close look, right, these three pods all belong to the same microservice. And this is just for example purposes, right? All of these product page pods belong to the same product page microservice. And if you look at the node it's being assigned to, all of these pods are assigned to the same node. And more so, it's all assigned to the same preemptible node. So in the scenario where this node gets preempted, what that means is all three of your pods, your entire microservice is down until these pods are rescheduled onto a different node. Now, how do you avoid this scenario? Well, someone might say, why don't you just use anti-affinity? And that was the first thing we tried, by the way. So anti-affinity actually tells the scheduler not to schedule multiple pods on the same nodes, right? Multiple of the same type of pods on the same nodes. However, when we were going with this approach, we noticed there were a lot of scheduling errors and a lot of the pods remained unscheduled because of us using this anti-affinity. And we thought there's got to be a better way to do this. And there was, right? So what we actually did is we created a custom scheduler, right? So GKE actually gives you that ability to actually incorporate a lot of customizations. So including at the scheduler level. So I created a custom scheduler of my own. And I said, you know what? This custom scheduler, I'm going to tell the scheduler to prioritize spreading the pods. So just as an FYI for you guys, the default Kubernetes scheduler, I'm not talking about GKE, I'm just talking about Kubernetes in general. So the default Kubernetes scheduler always prefers to spread pods based on node utilization, right? It gives a different weightage to each priority, but the highest weightage is usually given to spreading the node utilization. And what I did was I just downloaded the binary and I changed a few parameters here and there. I told the scheduler, look, what I want you to do is I want you to focus more on spreading the nodes, spreading the pods across nodes. Don't ignore node utilization. You can still prioritize that. Just give a higher priority to making sure that the pods are spread across multiple nodes. And I've even written a blog about this on our engineering channel. Sears has an engineering Medium blog. You can go ahead and take a look at this. If this is something you want to implement for yourself, it's a good way to start. And here's the result of that implementation. So before you can see that all these microservice pods are within the same node. After implementing the custom scheduler, you've noticed that these pods are now spread across different preemptible nodes, which is the best case scenario for us, right? So if one node gets preempted, no matter, I have two other replicas and two other different nodes. And don't worry, you can still use the default scheduler. So this particular scheduler which I used, I configured it in such a way that only certain microservices use the custom scheduler. For the remaining applications and microservices, you can continue to use the default scheduler. You can actually explicitly say that I want these particular workloads to use the custom scheduler, and the remaining can use the default scheduler. And by implementing all these different availability and reliability strategies, right? So when we were initially discussing with Nodescape, cost was one factor, but there was also performance. Like I said, they'd already performed a migration before. They had a bunch of benchmarks and metrics defined and organized, right? And these were mostly back-end latency metrics. And they said that one thing is the cost, right? But we do not want to compromise on performance. So if you can either match the performance or better it, that would be great. And after running our load testing on 26 different microservices, right, we ended up with a result of an 11% increase in performance. And when I say increase in performance, I mean an 11% decrease in backend application latency. So this is actually very, very advantageous, especially for a customer like Nodescape, where they have these cognitive games and 0% downtime. Not only are they getting this huge cost benefit, they're also seeing an increase in performance, right? It's a win-win situation. There's no two ways around it. And that's actually how we address the availability and reliability challenges using PVMs. Now, a slightly underrated aspect of Kubernetes in general is the cluster security. And so I'm going to talk a bit about certain best practices which you should be implementing at a minimum to ensure that your cluster is secure and it meets the standards of CIS. So I'm going to cover 3 certain best practices. One is tightening your network infrastructure in GKE. And I think of all the different security best practices I'm going to talk about, I think that is definitely by far the most important. Second is making the right container node choices. And third, using IAM, RBAC, and workload identity. So we're going to talk about tightening network infrastructure security on GKE. So CIS has a bunch of recommended benchmarks for Kubernetes, and it has a separate benchmark list for GKE. Right? CIS is the center of internet security, and they put out a bunch of checklists that should be filled out to make sure that you are compliant with their security standards. So I'm not going to go through the entire checklist. It's I think 100 item points long. I'm not going to I have a certain value for your time as well as mine, so I'm not going to waste time on that. But I'm going to talk about some of the important checklists that have to be filled out. So one is actually limiting the exposure of your cluster control plane and the nodes to the internet, right? So when I'm talking about the cluster control plane, I'm actually talking about the master nodes API server, right? So by default, this is actually, it's a public IP address. It can be accessed from any internet endpoint all over the globe. Right? This is the default configuration. So there are 3 different kinds of security settings you can set while creating your cluster. So this is in ascending order of tightness and security, right? With A being the least restrictive and C being the most restrictive. So the first point is actually keep public endpoint access enabled and master authorized networks disabled. This basically means that, I'm keeping my API server public and open and anyone can use it, right? I can sit on my laptop right now and I can do a kubectl command on this cluster, even if I'm sitting somewhere in China, right? As long as I have access to the internet. And this is the least secure option. And it's enabled by default, right? So that's the problem. Because it's enabled by default, I actually see a lot of people use this in their production environments. I know it sounds crazy, right? And it sounds something really silly, but you do see people actually do this. And it's something that I thought I should point out here. So the second approach is slightly more restrictive. It's the recommended approach also. Not recommended by me, recommended by Google. I would actually recommend the third approach. So the second approach is actually keep your public endpoint access enabled. So your master API server still has a public IP endpoint, but here you're actually whitelisting certain IP addresses and allowing only these IP addresses to access the API server, right? So this is perfectly viable solution. It's secure, it's fine. But if you're dealing with something like a fintech company or any kind of company where compliance and security is a must for you, then you might not want to consider this option because there are workarounds to actually, hack the system. You can actually do IP spoofing and things like that, which can actually cause a lot of problems in the future. The most restrictive option and the best option for, especially for fintechs and other companies which want to focus on security, is the last option where you disable the public endpoint access and you whitelist certain IP ranges. So here your master no longer has a public IP address, right? The API server no longer has a public IP endpoint. Rather, the IP endpoint is only private and it's only accessible by certain other private IP endpoints that you whitelist. And these other IP endpoints might be from your on-premises network, which is connected by VPN. It might be from a Bastion host, which you keep on the same cloud, right? It can be anything, as long as you need to have private connection to the GKE cluster, right? There is no traversal of requests or data over the internet here. The second security choice is choosing the right container, right? So I'm going to talk a bit about shielded GKE nodes. So this comes as a checkbox when you're creating your cluster. And some of you might have seen it while creating a cluster, if at all you've gone down that path. And you might be wondering, what does this actually do? So there are malicious attacks on Kubernetes environments that take a form of a Trojan horse kind of attack, where your malicious user actually infiltrates your cluster by disguising a node of their own and pretending that node is part of your Kubernetes cluster, and post which, after gaining access to certain security permissions, starts taking advantage of the system, right? So what shielded GKE nodes does is Google actually provides a strong cryptographic identity check on each and every node. Basically, what this does is it verifies that each and every node which is spun up on your cluster actually belongs to Google, right? It actually is part of your GKE environment. And the backend is entirely abstracted from you. For you, like, all you have to do is click a single checkbox. But it's an important security feature which you should be having. Another thing is choosing the right container node choices, right? So Google actually has worked on optimizing a container image that's specifically meant to minimize attacks, focus on security, and make it as lightweight as possible. So they've actually put out this very lightweight OS called Cost Container D, right? It has a very minimal OS, so that means there's very less surface area for attack. And actually using this kind of image, it's an already hardened image by GCP, right? It prevents rootkit and bootkit malwares. It's not just a security thing, it actually improves the performance of your application as well, because now the underlying OS, which the pods are using, is actually very lightweight, right? So it leaves more space for your application's base OS. Moving on to IAM secrets and permissions. So step one, I mean, anyone who's worked in security is familiar with the principle of least privilege, right? And this applies at every level. It applies at an IAM level, it applies at a networking level, right? Only assign privileges as strictly as possible, you know? Make sure that no one has more permissions than they should be having. And that same methodology is actually implemented here. So your GKE nodes, right, are actually tagged with service accounts, and these service accounts have certain permissions assigned to them. So normally when you create a Kubernetes cluster and you leave some of the settings in default, you can actually end up using the compute engine default service account. Now, this compute engine default service account actually has a lot of permissions. In some cases, it even has editor permissions. So basically, this allows anyone who logs into any one of your Kubernetes nodes, it will give them the access to create a Cloud SQL database, delete a database, delete some data in a GCS bucket, create a new bucket, right? A lot of potential human error or malicious activities can be caused due to this overly privileged service account. So what Google tells us that at a minimum, your service account really actually requires only 4 kind of roles. One is the monitoring viewer role, the monitoring metric writer role, the logging log writer role, and if you're using private images in a GCR repository, you will also want the storage object viewer role. All the other roles are secondary, right? They are over-privileged. It's not something the Kubernetes node actually needs. Now, you might be thinking in your mind, but say I want to create a pod that has access to Cloud SQL, or I want to create a pod which has permissions to write on a cloud storage bucket, right? What do I do in that case? My node doesn't have the right permissions. And that's where we begin the conversation about workload identity, right? So this is another new feature that Google has put out, and frankly speaking, it's a very cool feature. I've been waiting for it for a while, right? And basically what this feature says is it allows you to tag a Google service account with a Kubernetes service account. So let's go back to that same example where I want a certain pod of mine or certain deployment of mine to access a Cloud SQL database. So what I can do is I can create a service account on Google Cloud, a Google service account, and I will give it the permission to access Cloud SQL. Now that same Google Cloud Service account, using workload identity, I can actually bind that Google Cloud Service account to a Kubernetes service account. By binding the GKE service account to the Kubernetes service account, the Kubernetes service account is actually leveraging the permissions of the Google service account. And furthermore, that Kubernetes service account can be binded to or bound to a particular application or pod or deployment. So for that particular deployment, which actually requires Cloud SQL, I would use that Kubernetes service account, which is bound to a Google Cloud service account, which has the right permissions. And all of this is done through workload identity. It's a cool new feature. I think it's something that for those of you who are more into security, it's something you should test out and try using. It's going to actually prevent a lot of. I see a lot of cases, where sometimes an application has deleted a table or it actually deletes some data in a GCS pod, and it actually prevents such scenarios from happening. So it's a good measure to take. And that is the last segment for our security discussion. And I hope it's been really insightful and thought-provoking for you, how we've actually taken these different things, starting with using PVMs, which are so much cheaper but have so many drawbacks, and then tackling these drawbacks one by one and actually leveraging the PVMs despite all the drawbacks, and making sure that we're having a best practice environment that has availability, reliability, and performance. And most of all, on top of that, you get a huge discount on your cost. So I think these kind of different strategies that we've taken, right? It's come through a lot of years of experience that we've had on Kubernetes and on GKE and on GCP in general. And it's something that we love implementing for our customers. We always try to think out of the box and make sure that we follow through on what we propose.
Thank you, everyone. Take care. Cheers.